Welcome to day 28, and today's episode is brought to you by our good friend Bill. Bill, as in the magnetic force on a wire is equal to the magnetic field the wire is in times the current through the wire times the length of the wire. Regardless, what we really want to take a look at today is just a little more with regards to potential difference. And we're going to talk about a few different things. First of all, let's talk about our favorite piece of electrical apparatus again, a pair of large oppositely charged plates that are connected to a battery. You saw this yesterday, and here's a picture of some right now. Ignore the green for starters, we'll get to that in a bit. So here's a pair of parallel plates that are hooked to a battery, and you can see here's our battery. It's a 12 volter, likely a car battery. There's the positive terminal of the battery. It's basically just going to be a big buildup of positive charge. There's a negative terminal of the battery. It's going to be a big buildup of negative charge. And of course, the positive terminal of the battery, it attracts negatives off the top plate, leaves a bunch of lonely protons, a bunch of positive charges in the top plate, and it takes these electrons and it does work on them from here to here, and once they get to here, the negative concentration of charge on the negative terminal of the battery, it repels these electrons onto the bottom plate. Okay. And of course, what you've got here is, our favorite piece of electrical apparatus, right? A pair of large oppositely charged parallel plates. They're hooked to a battery, and if you have plates like this hooked to a battery, well, the electric field runs from the positive to the negative in a nice straight line, okay, just like it's supposed to. Okay. The electric field is the same everywhere. It doesn't matter whether you're here, here. The electric field is uniform throughout. Okay, that's no problem. However, this is a little different. Remember when we talked about, or when we originally talked about large oppositely charged parallel plates, the plates weren't connected to a battery. And if plates aren't connected to a battery, their separation has no effect on the electric field, okay? If the plates aren't connected to a battery, separation has no effect on the electric field. But if the plates are connected to a battery, like these one here, the separation, it does affect the electric field between them. If you push the plates closer together, the field gets stronger. If you pull the plates further apart, the field gets weaker. And let's see if we can figure out just why that is, okay? So here's our parallel plates. We got a positive charge on top, equal but opposite negative charge on the bottom. Okay, some electric field in between them. Now let's see what happens if we push these plates closer together. So now these plates, they're in the position shown by the green here. What's going to be going on there? Well, I'll tell you what. The bottom plate, the negative plate, it's a lot closer to the top plate, the positive plate. So not only are the electrons in the top plate being pulled by the positive terminal of the battery, but they're also being pushed with a lot stronger force from these negatives down here. These negatives, they used to be way down here, they're pushing on the electrons up here very weakly, while now they're a lot closer. Now these negatives, they're pushing on the electrons in the positive plate with a lot more force. As a result, more negatives are going to leave the top plate, and the top plate is going to have a much larger positive charge. And of course, these negatives, well, they're going to wind up with the electrons from the top plate, they're going to wind up on the bottom plate. So the bottom plate is now going to have a much larger charge. And you might remember, from when we originally talked about large oppositely charged parallel plates. If you increase the charge on the plates, you increase the electric field. So you move the plates closer together. These negatives down here are now pushing much harder on the electrons in the top plate, and you get a migration of electrons from the top plate to the bottom plate. Bigger charges, more electric field. You might want to hit pause and make a note of that somewhere. It is fairly important. And of course, you can imagine what happens if you pull the plates further apart. If you pull the plates further apart, well, now the negatives down here, they're going to be exerting less of a force on the electrons in the positive plate. So less electrons are going to migrate from the top plate down to the bottom, and you're going to have a smaller charge on each plate. Okay. Bottom line, what you have to remember, no battery involved. Plate separation has no effect on electric field. With the battery, okay, plates come closer together, the electric field gets bigger. Plates get further apart, the electric field gets smaller. Okay, you've probably had enough of that one. Let's move on to something else. Okay, again, this is going to look quite familiar. This is something we looked at yesterday, and we actually did this calculation yesterday. Okay, we had a pair of oppositely charged plates separated by some distance d. Okay, there's some electric field in between these plates. Okay, and what we want to do is we want to calculate the potential difference in between these plates. We actually did that yesterday, but yesterday we did it with very specific numbers. Today we're going to do it in more general terms. So, two plates separated by some distance d, there's some electric field between them. What's the potential difference between these plates? Okay. Well, you might remember that if you take a charge and you drag it from one plate to another, well, the work you do on the charge is equal to the charge times the potential difference between the plates, right? Take this charge, do some work on it, drag it from one plate to the other, W equals QV. Now remember, when we're doing work on this charge, the work done on the charge is going to be equal to the force times the distance. Okay, so we got to exert some force on this charge as we're dragging it through some distance d. And remember, if we drag this charge at a nice constant velocity, the force we exert on it has got to cancel off the electric force. Okay? The force we exert on it, it has basically got to cancel off the electric force. It's got to be the same as the electric force. The force of these negatives pulling the charge down, and the force of these positives pulling the charge down. So the force we're exerting on the charge is the same as this one, F.E. Okay, so there's where we're sitting now. The electric force times the distance is equal to QV. Well, what do we know about the electric force in the charge? Well, how about this? The electric field is equal to the electric force divided by the charge. It's just a little bit of review, right? You learned that way back last year. The electric field is equal to the electric force divided by the charge. You rearrange this equation ever so slightly, take the Q over to the other side, and there you go. The electric field times the charge is equal to the electric force. So let's substitute this in for this. The electric force is equal to the electric field times the charge. And then you're multiplying by the distance. You got QV on the other side. And pardon me, and I'm pretty sure you know what's coming next. These Q's, they annihilate each other off the face of the earth. There is what you're left with. The potential difference is equal to the electric field times the distance. Okay? V equals N. You know Bill? Okay, from magnetism, well, this is Bill's cousin Ed, V equals N. And you've got to remember that this equation, okay, it's good in a situation like this where the electric field is uniform. As long as the electric field is uniform, as long as it's staying the same over the whole distance, okay, like between a pair of parallel plates, this formula is fantastic. V equals N. We will do an example, or maybe even a couple examples, using this idea and maybe a couple others in just a bit. All right, here's a nice little problem to do. Two plates are hooked to a battery and separated by 7.5 centimeters. The electric field between them is 150 newtons per coulomb. Find the new electric field if their separation is decreased to 5 centimeters. So here's a diagram of what's going on. Here we have our two plates connected to a battery. You'll notice the positive plate is connected to the positive terminal of the battery. The big line is always positive in a situation like this. And of course, the negative plate connected to the little line, the negative terminal of the battery. Separation, 7.5 centimeters. Electric field between them. Of course, electric field is going to be going down because if you stuck a positive charge in here, you didn't want to go down. Electric field 150 newtons per coulomb. Okay, okay, so what's happening here? Well, we're changing our separation, right? Our separation is becoming 5 centimeters. So we're going to have a new separation of 5 centimeters. What is our new electric field going to be? Let's see if we can figure out how to do that. Well, how about this? What do I know about this situation? Well, I know that V equals N. Write down what we know. V equals N. Okay. The electric field is 150. The distance is 7.5 centimeters. Now remember, this 150 is in base units, newtons per coulomb. Remember, a newton is a kilogram meter per second squared. So there's actually meters tied up in this. So that means your distance, it's got to be in meters too. So we're going to change that that 7.5 centimeters to 0.075 meters. And there we go. Do the multiplication and you get, I believe, 11.25 volts. So the voltage of this battery is 11.25 volts. And remember that if there's 11.25 volts across the terminals of the battery, there's 11.25 volts across the terminals, across the plates. That's something that we talked about a little while ago. Whatever this voltage is here, in this case 11.25, you're going to have the same voltage between here and here. Okay, so, well, how about we apply the exact same equation again? V equals N. Okay. We move our plates closer together, so the new distance is going to be, instead of 7.5 centimeters, it's going to be 5 centimeters, so the new distance is going to be 0.05. The new electric field, well, that's what we're trying to find. And I guess if I really want to be consistent here, I should say that what we're dealing with here is now E prime and D prime, right? D prime is 5 centimeters and E prime is what we're trying to find. Okay. What's the voltage? Well, they're still hooked up to the same battery. They're still hooked up to this 11.25 volt battery, so that means the voltage between these two plates is still going to be 11.25 volts. Okay. And you solve this equation, this goes across the other side, goes downstairs, you solve this equation, and you're going to get and electric field, I believe it's 225 newtons per coulomb. And if you want to be really thorough about it, you realize electric field is a vector, and the direction would be towards a negative plate. Done. Let's take a look at just a slightly different way of doing this. Okay, let's take a look at just a slightly different way of doing this, maybe a little shorter. Here's how some people might like to do it. Okay. Some people, they look at this problem and they'd say, okay, look, you're fiddling around with D, well, what's going to happen with E? And they think, I've done those problems before. You know, you play around with one side of the equation, what's the effect on the other side of the equation? So what's an equation that is governing this situation? Well, it's of course this one. The voltage across the plates, or the potential difference across the plates, is equal to the electric field times the distance. And remember, we are interested in electric field, right? That's what we're trying to solve for. We are interested in electric field. So let's solve this equation for electric field. The D goes over to the other side, it's going to go downstairs. And when you solve this equation, you're going to get the electric field is equal to V over D. Okay? Now, you got to remember, D is changing, it's getting smaller. E is changing, we're trying to figure out what the new E is. But the voltage is staying the same. The potential difference is staying the same. Doesn't matter what you do to your plate separation here, that battery is still hooked up. That means the potential difference between the plates is always going to be the same. So this V, it is constant. The plates are always hooked up to that battery, and the voltage of the battery isn't changing. The potential difference across the plates is not changing. Okay, so E is equal to some constant divided by D. Well, what's happening to D here? It's being reduced by some factor. Let's see, 7.5 divided by 5. That's 1.5, right? 7.5 divided by 5 is 1.5. So D is being reduced by a factor of 1.5. So what's going to happen to E? Well, this one's on the bottom, so whatever happens here, the opposite's going to happen over here. E is going to get multiplied by a factor of 1.5. So your new electric field is going to be your old electric field, which is 150 times 1.5. And you can try that on your calculator. 1.5 times 150, 225 newtons per coulomb. Again, towards a negative plate. Slightly different way, again, this same answer. And I know I explained it in great detail, so it probably took longer, but if you realize this is the way that it works, it's actually maybe a little quicker. However you like to do it, that is up to you. We will try one more example. An example now. What does it say? It says find the potential energy in joules of an electron with respect to A at, first of all, point A, and then again at point B, which would be here. So again, you can see we've got our favorite piece of electrical apparatus, paired charge plates. They are connected to a 150 volt battery, so that means the potential difference between the plates is 150 volts. And we're trying to find, just like it says, the potential energy of an electron with respect to A when it is at A. Well, imagine you've got an electron, you're hanging on to it in position A there, you let go of it, what happens to it? Absolutely nothing. These negatives are going to keep it pinned at position A. These positives are also going to keep it pinned at position A. So that electron, it is basically stuck in position A. You let it go, nothing happens to it. It doesn't move on its own. Remember, if you pick something up in a gravitational field and you let it go, it moves. That means it's got potential energy. Here, the electron is stuck at A, you let it go, nothing happens to it. So the electron's potential energy at A, well, that's easy. It's equal to 0. No calculation needed there. Okay. Now how about the potential energy of the electron with respect to A at position B? Okay, that is maybe a little bit more involved. So think about your electron. Okay. You got a hold of it in position A, and then you pull it, and remember, you got to do work on it to get it to position B, because the positives are trying to pull it up, the negatives are trying to push it up. You got to do work on it to pull it in to position B. Once it's in position B, you let it go, and it just flies on its own back toward the positive plate. So it definitely has potential energy at B, right? Because let's face it, when you let it go from position B, it's moving on its own back up to where it was originally, just like this brush. I let it go, it moves on its own back to where it was originally. Okay, so we know this thing, this electron, it definitely has potential energy at position B. The question is, how much potential energy does it have? Okay. Well, how about this? To get it to position B, I got to do work on it. The work I do on it, that's going to be equal to the potential energy it has. So the potential energy of B, that's going to be equal to the work I do on it to get it to position B. And how do you figure out the work you do on this thing to get it from here to here? Okay. Force times distance probably isn't going to help you very much here. Probably this is what you want, right? The work on a charge is equal to the charge itself multiplied by the potential difference you move it through. So the work done on our charge is equal to the charge itself, okay, times the potential difference we move it through. And we're looking for, remember, the potential difference between these 2 points. That is not going to be 150 volts. Remember, the potential difference between the plates, between these 2 points, is 150 volts. We just want the potential difference between these 2 points. That is not going to be 150 volts. How can we figure out what the potential difference is between these 2 points? Well, how about this? What do we know about this situation? We know that the potential difference between the plates is equal to the electric field between the plates multiplied by the distance between the plates. Okay, that's nothing new, right? V equals that. The potential difference between the plates is equal to the electric field between the plates times the distance between the plates. And you got to remember that the electric field is constant. No matter where you are, the electric field is constant. It is staying the same. So look at this mathematically. The potential difference is equal to some constant times the distance. The potential difference is equal to some constant times the distance. The potential difference is proportional to the distance. the potential difference is proportional to the distance. So that means, basically, that you can write ratios between these two things. Remember, if things are proportional, you can write ratios between them. So how about this? How about this? I'm going to say, remember, I'm trying to figure out VAB. Okay, so how about this? I'm going to say the little voltage, VAB, the one I'm interested in, is to the big voltage. Okay, that's the 150 volts. As the little distance, 10 centimeters, is to the big distance, 15 centimeters. Okay. Hopefully everybody's okay with that. The little voltage, VAB, is to the big voltage, 150 volts, as the little distance, 10 centimeters, is to the big distance, 15 centimeters. Okay. And, oh, that's easy to solve. 100 over 150 is the same as 10 over 15. So, we know the VAB is equal to 100 volts. Okay? So we're pretty much there. What's the potential energy of our electron at B? Well, it's equal to the work, QV, Q. Remember, if your voltage is in volts, a volt is a joule per coulomb, your charge has to be in coulombs. So we have an electron, which is the equivalent of one elementary charge, 1.6 times 10 to the minus 19 coulombs, multiplied by our potential difference, 100 volts. And you can grind this through your calculator or realize that 100 is the same as 10 squared. Add the exponents here and you get 1.6 times 10 to the minus 17 joules. Done. Okay. And I guess the moral of this story is, if you're in between charged plates, the potential difference is going to be proportional to the distance. You can write ratios involving potential differences and distances here. All right, you will have an assignment posted on this. Make sure you do it. It'll hopefully solidify a bunch of these things in your mind. Good luck. Bye for now.